In the winter of 2015, the United States, along with other countries, went to the United Nations Global Climate Conference called COP21, and the United States pledged to reduce carbon emissions by 28% by the year 2025. The reason that Minnesota legislation has some utilities shifting to 20% renewables by the year 2020 is because electrical generation is one of the leading contributors to carbon emissions, and wind energy is one of the ways that Minnesota can help reach this renewable energy's goal.
Both federal and Minnesota policy offer incentives for those wishing to transition to renewables. For those who wish to start wind farms, federal offers 2.3 cents per kilowatt hour of electricity generated at a wind farm, or a tax credit for 30% of the value of the utility scale facility. Likewise, Minnesota offers property tax exemption for wind farms. There are many siting regulations for wind facilities. Airports have a 20,000 feet buffer from all runways, and meteorological towers have a buffer of 250 feet. Within the farm, there's a boundary buffer and turbine spacing of 3 rotor diameters. For roads and recreation areas, there's a 250 feet buffer, and residential areas have a 500 feet buffer. Likewise, all public wetlands and native prairie, as well as private sand and gravel operations, are exempt.
We had 3 main goals for our project. The first was to target optimal locations for wind farms in Minnesota based on both profitability and those exclusion zones that we heard about a little bit earlier. Second, we wanted to calculate the land area required to meet that 20% renewable energy production goal in Minnesota. And thirdly, we were going to estimate the proportion of land dedicated to wind infrastructure based on a study of existing wind farms. To answer our first question, we wanted to come at it from 2 different directions, both profitability and regulations. Those would create 2 different map layers, one of profitability, the other of sites that meet regulations. So on the left we have the excluded areas model from ArcGIS. In blue we have our input data layers. Those include protected lands, population centers, airports, lakes, and roads. And in the end we created an excluded areas map that we'll look at a little bit later. On the right we have our profitability map, and into that we put Minnesota lights at night, which was a proxy for population density. We also had 100-meter wind and distance to substations, and in the end we got a profitability map. So here's our exclusion map. Everything in red is what is excluded based on Minnesota regulations. And this is our profitability map. Everything in red is what is most profitable, and everything that goes towards the blue end is going to be less profitable. And in the end we created this map. Everything in gray that you see is areas that we're excluding because they aren't profitable and they don't meet the regulations. Everything that's yellow and red is going to be that which meets both Minnesota siting regulations and profitability standards.
Our second research question focused on calculating the land area required to meet the 20% renewable energy goal for Minnesota. To do this, we looked at the total power production in Minnesota, around 120 million megawatt hours, and calculated that by the 20% needed to receive about 24 million megawatt hours that we need to be producing with renewable sources. Currently, Minnesota already produces 9.8 million megawatt hours through wind generation, leaving us about 14 million megawatt hours needed from our proposed wind farm. Dividing this by the number of hours per year, and we get about a 1,600 megawatt capacity wind farm. The second part of this research question focuses on the amount of land needed per wind farm, looking at 2 different models. The 2.5 megawatt model is an industry standard currently, while the 5 megawatt model would be a future and emerging technology. Then, using the siting regulations outlined earlier, we calculated that each turbine would need about 0.128 and 0.234 square kilometers respectively. Multiplying that by the amount of turbines based on the capacity wind farm, we receive about 271 square kilometers for 2.5 megawatt installations and 247 square kilometers for 5 megawatt installations. This is what that would look like visually. The majority of the wind farms are located in the southwestern part of the state, along Buffalo Ridge, around some of the more shallow lakes in the area. It's important to note that the land use required by this wind farm is only available at these highest production areas. Putting the wind farm in one large area or in another part of the state would require more land because it isn't as an efficient area. 271 kilometers squared is about half the area of Lake Mille Lacs, shown in the central part of the state. This is what the 5 megawatt installations would look like. Notice that the land use required by both the 2.5 and the 5 megawatt turbines is minimal.
The results of our model show that optimal siting is located on lake shores and other areas near Buffalo Ridge in southwestern Minnesota. There's only a small difference between the 2.5 megawatt and 5 megawatt wind turbine areas, according to our model. According to literature, about 2 to 5% of total area is used by wind turbines. So with this, our proposed wind siting from this work would only cover 15 square kilometers of the ground. The primary problem that we were addressing with our model is that wind turbine development may lead to extensive land use, habitat fragmentation, and direct wildlife impacts. In order to address this, we determined the most profitable areas so that we could minimize land use, which in turn preserves native habitats and prevents issues like wildlife mortality and habitat fragmentation. And as a result, we can also meet the 20% renewables goal in the state of Minnesota while using less land. We identified a few things for future research. One thing was with future technological advances, there's a trade-off between generating electricity with large turbines that take up more space or generating electricity with small turbines that can be packed together, and just exploring the trade-off between these two possibilities, as well as investigating the impact on species in southern Minnesota and how these are impacted by wind turbine placement, especially migratory birds. Our model had a few caveats. One is infrastructure and power line expansion, which we're not taking account into the model, but when you build wind turbines, and especially large wind farms, extensive land is needed for power line expansion that we did not account for. Also, we did not account for the topography of the landscape. Certain slopes and other features on the landscape can't support wind turbines, which we did not take into account. And additionally, local support, things like county level regulations and cooperation between utilities and local government were not taken into account. Just the assumption that wind farms will be supported by local communities, although that's not always the case, and they're not always possible due to local and county level regulations.